look at both of them. So if we make A the axis, then this is going to rotate this way around A, right? That's going to be a counterclockwise rotation, so we're going to have a positive torque. So first thing is, let's draw the line of action. Remember, that goes collinear with the force. And then your lever arm goes from the axis to the line of action. So there's our lever arm. This is the right angle there. Okay, now the torque for the force here around A, Fr sine theta. So F is 110. R is going to be the distance from forces applied to the axis, so 0.76. And the angle is 90. So that gives us about 84 newton meters. So that's when the axis is around A. Now if instead we make the axis around B, it's going to rotate this way, which is a negative rotation. So we make that negative. So now we do torque Fr sine theta. So 110. Now R, again, linear distance axis to force is 1.4 sine of 90. Here's our lever arm, by the way. I didn't draw it in there, but there's your lever arm there. And so that is 154 newton meters, but because it's going to be negative, we need to make it negative. Okay. So the concept we want to focus on in this question here is net torque, because that's going to lead us into the next thing we're going to talk about. So what do we have for an answer? Anyone yet? Alex?
1702 newton meters.
Right, 1702 newton meters. Now, are their torques in the same direction or opposite? Same, right? Both of them are going to cause counterclockwise rotations, so they're both going to be
Positive.
Applying positive torques. If the one guy came over here, then there would be no net torque, right? If you pushed with the same amount of force over here, then it won't rotate. So we'll calculate the torque for one guy and then multiply it by 2. Since it's the same force and the same distances, it'll be the same torque. So line of action through the force, axis to the line of action gives us the lever arm. Now you get the torque for the guy on the right. So Fr sine theta. So his force is 185. R for him would be half of the length of the car, 4.6. And then you got your 90. So sine of 90. And so you get 851 newton meters. And this guy over here is going to do the same exact thing. So just times this by 2 in this case. You get 1702 newton meters. Okay, so you want to look at the net torque, which is the sum of all torque. So in this case, there's 2 of them. So we multiplied it by 2. Right? So now we want to have what causes an angular acceleration. If both of these guys were pushing the car, and they kept pushing it, and kept pushing it, and they're running with it in a circle and kept pushing it, what would the car do? It'll rotate, but it'll keep getting faster, right? It'll accelerate as it rotates, right? As long as they keep applying their torques, they'll keep getting faster and faster and faster and faster. Okay, so if we keep applying a net force to something, it accelerates and it keeps getting faster and faster. Likewise, if we continue to apply a net torque, so now we want to do Newton's second law for rotation. So the net torque, so that's going to be the counterpart to net force, net torque, is going to equal something times what? What quantity? What letter? The fish, right? Alpha. For acceleration. I'm hoping to catch it in the bucket there. All right, here we go. first.
How?
I don't know. How does this work? Let's make sure it works again.
Password. It doesn't cancel.
Oh, I turned it again.
If you push them, would the metal one go farther? Faster down?
If I push them, do I push them with the same force? If I push them with the same force, then the same thing will happen.
I feel like the wooden one was a little heavier though. I don't know.
Don't start with me. No, it wasn't. It's not heavier.
Like,
That's what the
maybe
catalog
exact-
said.
Can we get out of scale?
That's what the catalog says.
Let's mask them on the.
How long have you had those and you've never measured them?
I haven't. I have not measured them. That's all part of the demonstrations. They're the same mass. So you gotta just trust me on this.
Okay.
So why does this happen? Let's talk about why it rolls down first. Why does this roll down?
Like she said, magic.
Magic, no.
No, it's on a hill.
Can be explained by physics.
Physics is magic.
Gravity. Okay. So what is the first, when I put this on here and let go, what is the first thing it wants to do? Gravity's pulling it what way?
Straight down.
Well, straight down, but right. Think of it as a component. One's going into the board, the other one's going parallel. When I put this on, when I put it like this, what does it want to do? It wants to slide, right? Gravity's trying to slide it down, and it doesn't slide because friction going that way. Okay. So when I put this here, it actually wants to do what? Slide down. Right? It wants to slide down. If this was ice, I would put it on here, and there's a good chance it would just slide right down. So, it doesn't slide. So it says, oops, I can't slide. So what happens next?
Starts to roll.
It rolls. Why? How do you make something roll? How do you make something rotate? Not a force. A torque, right? You got to put a torque on this. To make anything roll, to make anything rotate, you got to put a torque on it. So where's the torque coming from?
Gravity.
Let's think about this. It wants to slide down, and it can't. Right? It's trying to slide, and it can't. So static friction is pushing it which way? That way, at this point, right? Where's the axis of rotation? Right in the middle. So something is actually pushing it to rotate around my finger. That something is static friction. So as it tries to roll, it can't, and it gets basically torqued, and that just keeps happening the whole way down. Okay? So both of these are receiving a torque as they roll down. Which one has a greater alpha?
The wooden one.
The wooden one. How do you know that?
Oh, it's still mad.
Because it gets down there first. So that means it's rolling faster. It has a greater rate of rotation. So its alpha is higher. So if they have the same torque and they don't have the same alpha, that means that they don't have the same I. It's different. What is I? I describes how something responds to a torque. Just like mass describes how something responds to a force. So what does I stand for? Jeff? Inertia. So what's inertia? Anybody remember what inertia is?
Not not
It's an object just like in a desire to keep moving.
To keep moving, to not change its state of motion. So if it is moving, it wants to keep moving. If it's not moving, it doesn't want to move. These start out not moving, right? Which one doesn't want to move more? The metal one, right? So its I must be higher. And that's why it has a lower acceleration. So I'm going to pass these 2 meter sticks around. On the meter stick, I have a half a roll of nickels here and a half roll of nickels here. Don't steal them. I want you to grab them at the 50 centimeter mark and do this. Okay. This meter stick symbolizes this ring. Okay. As it wants to roll. That's what this is doing. All the mass is on the outside, far away from the axis. I have another meter stick has half roll of nickels, but much closer to the axis. That symbolizes this, the mass distribution in this. And I want you to do this, okay? And see which one feels easier to rotate, okay? And then think about that these are both trying to do that. And this one is easier to rotate because of the distribution of mass. Now when you do it, don't hit your partner in the head. Don't poke their eye out, but just feel it. You'll see how easy it is to change the direction of this one compared to this one. And it's because this one has a lower value of I than this one. Moment of inertia, right? You're going to need to refer to tables. Right? All these moments are already calculated for you. You just have to refer to a table. Trevor?
Doesn't Mr. Smith have that thing where you can stand on it and he spins you and then you put your arms out?
Yep. We're gonna get to that in this chapter.
We're gonna do it.
We'll do it. Yeah, in the next section. That's exactly what this is, though. Exactly.
I'm really excited. I'm really excited.
Now, the moment of inertia depends on how the mass is distributed. So now let's look here. If you have a thin hoop of radius r, and this is page 206 in your book, by the way, but if you have a thin hoop of radius r, like this, and the axis is through the center, so here, and it's rotating around that axis, to calculate the moment of inertia, you use the equation mr squared. If you have a solid disk, like this, and the axis is in the center, so it's rotating in the center, you calculate the moment of inertia 1/2 mr squared. Okay, so it all depends on not only the shape of the object, but where the axis is in the object. Okay, and then just here's some other examples. You see that the disk has 1/2 the moment of inertia of the ring. So that explains why the disk rolls down faster, right? It has less moment of inertia. All right, so now with that being said, let's try an example. First thing I did was I calculated the net torque. So there's two torques on here. This is the one from the 125. It's negative because it's clockwise, and then I add to that the other torque. So the torque is the first thing I calculated. Now, to get the acceleration, I want to use Newton's second law. So I need I alpha. I already have the torque. Right? So I need to get I, so I can then get alpha. So I is, and this is going to be a solid disk, which you see on page 106 is 1/2 mr squared. So you want to put in 1/2. The mass is 24.3, and R is 0.314, and you have to square that. So you get 1.20 kilogram meters squared. So this value will go in here for I, and the torque will go in here for the net torque. So now you have negative 11 equals 1.20 alpha. So alpha is negative 9.2 radians per second squared. If I gave you, I'm not going to ask you to do this, but let's say I gave you omega I and a time, you could then find omega f, right? Because you have acceleration, omega I and time, you could use this and get omega f.